Hello! Today we're going to go through LeetCode problem 35, which is search insert position. Let's look at the problem here. So basically it's saying, given a sorted array of distinct integers and a target value, return the index if the target is found. If not, you need to return the index where it would be if it were inserted in order. And you must write an algorithm with big O log of n, runtime complexity. Alright, let's look at some examples. In the first example, we have a nums array of 1, 3, 5, and 6, and the target number is 5. And this is, the output is 2, so if you look at the position, the indexes, you have 0, 1, 2, so 5 is at index 2. In the second example, you have 1, 3, 5, and 6. The target is 2. So you have index 0, and then the 2 should actually appear between 1 and 3, so that's why the output is 1 for index 1. In the third example, we have 1, 3, 5, and 6, and 7. And because 7 does not exist in the input, we're going to do 0, 1, 2, 3, and then put it at the end for index 4. Alright, for example 4 here, we see nums is 1, 3, 5, and 6, and the target is 0. So that is going to be at index 0, because it obviously comes before any of these other numbers. The last example, nums equals 1, target is 0, and this is also 0, like the previous example. It comes before the number 1. Alright. So let's go back to, before I do the pseudocode, I want to explain a binary search, because we're going to do this with a binary search. This is a new concept. It also adheres to the log of n time complexity that we need to use. So I think it's our best option. And it's a fun one, so hang on. Alright. So L0. So this is saying index 0. So to do a binary search, you assign a left value and a right value. And using the left and right, you determine the middle value. So L equals 0 for index 0 and R equals 6 for index 6. And the mid is going to be 6 plus 0 divided by 2, so it's going to be 3. So 0, 1, 2, 3. Mid, the value of mid is 4, and the target number we're looking for is 6. So because 6 is greater than 4, you assign, so it's basically divide and conquer. So you're going to slice the array in half. So we're going to take L is equal to the mid value plus 1. So because the mid value is 3, we're going to add 1, and so now L becomes 4. R is still the 6, and 6 plus 4 is 10 divided by 2 is 5. Now keep in mind, these are the index values, so because the array is now just 3 elements, they still keep the index numbers. So this is index 4, 5, and 6. Now, taking the mid value, and binary searches just hinge off the mid value. You're just going left or right based on if the target is greater than or less than the mid value. So in our case, the target value is 6 and the mid value is 7. So 6 is less than 7. So now we're going to take the right value and assign it to the mid value minus 1. And so R is 6, mid value is 5, minus 1 is 4. So L is 4, R is 4, and we get a target number of 6. So that's how a binary search works. Okay, so let's pseudocode this. So this is the method LeetCode gives us. So we're going to create a variable called left and assign it to 0, just like we saw in the previous slide. Then we're going to create a variable called right and assign it to the nums length minus 1, which is the rightmost index in the array. So then we're going to loop through each number while left is less than or equal to right. Because once we get right, once we get right greater than left, then they overlap, and then you definitely don't. You can't go any further than that. So we're going to create that variable called middle and assign it to left plus right divided by 2. If num's middle equals the target number, we're going to return the middle number. And this is the best case scenario. This is actually O of 1. Because if the target is equal to the middle value, then you return the middle number and you're done. So if num's middle is greater than the target number, we're going to make the right value equal middle minus 1. Else, if num's middle is less than the target number, we're going to take the left and equal middle plus 1. We end the loop, and then if we enter a case where the left is actually greater than the right, then we're just going to return the left. Alrighty, so let's code this for reals. Int left equals 0. Int right equals the num's length minus 1. So while left is less than or equal to right, which we saw in the pseudocode, we're going to assign the middle equal left plus right divided by 2. So if the num's middle equals the target, we're just going to return the middle. Else, if num's middle is greater than the target, then we're going to assign the right value, which is the index, equals the middle index minus 1. Else, left equals middle plus 1. So this else is basically when the num's middle is less than the target. Then we're in the loop and return the left value. And that is all she wrote. So let's go into IntelliJ and run this. Alright, so I used 1, 2, 3, 4, 5, 7 as the array, and the target is 6. So I've got to eventually stick 6 between 5 and 7. So let's run this. Assign int left equals 0, the right equals num's length minus 1. So while left is less than or equal to right, which is true in this case, the middle is going to be 5 plus 0 divided by 2, which will be 2. With integer values, it ignores the remainder. Okay, if num's middle equals the target, which it does not, else if num's middle is greater than the target, which it isn't. So now we're going to enter the case where num's middle is less than the target. So we're going to assign the left value equals middle plus 1. Middle value is 2 plus 1, so that will make the left equal to 3. Alright. So while left is less than or equal to right, which it is still, we'll assign the middle equal left plus right, which evaluates to 4. If num's middle equals target, which it doesn't, else if num's middle is greater than or equal to target, which it isn't. So in other words, we still have our target is still greater than the middle value. So we're going to assign the left value equals middle plus 1. So left value becomes 5. So now we enter into this case where left is actually equal to right. And so we have left plus right divided by 2, middle becomes 5. If num's middle equals target, which it doesn't, else if num's middle is greater than target, which it actually is. And so basically we have the left equals 5 and the right equals 5. So 0, 1, 2, 3, 4, 5. So 7. So 7 is actually greater than our target of 6. So we make the right equal middle minus 1. So now we have the right equal to 4 and left equal to 5. So then, okay, well that's false. So we're going to turn the left, which is 5. So if you look at the result, the target number was 6. So index 0, 1, 2, 3, 4, 5 is where the 6 needs to be placed. So that is the answer we're looking for. So let's go back into LeetCode and see how this works. So I have the code here. I'm going to run it, accept it, and submit it. Look at that. Once again, we are faster than 100%, which means we are the fastest submission. All right, so the memory usage is 38.8 megabytes, which is less than 51%, so about half. Yeah, we'll take what we can get. All right, so here comes the fun part. The time complexity is O log of n, which is logarithmic complexity. So what in the heck does that even mean? So let me try to explain logarithmic complexity. So big O uses what's called the worst case scenario. If you have the best case scenario, that's the fastest. So that would be O of 1, which we saw when the number was actually equal to the middle value. But that doesn't happen all the time. So big O uses the worst case scenario. So in that case, the number is either at the beginning of the array or at the end of the array. So we keep dividing stuff in half, and so we divide it, all the way down to the first or the last number. So let's say our array has 8 numbers. So we divide by 2 until we reach 1. So you have 8 divided by 2 is 4. You have 4 divided by 2 is 2. And then 2 divided by 2 is 1. So it takes 3 iterations. Another way to write this is 8 divided by 2 to the first, which is 2, equals 4. And then 8 divided by 2 to the second. So 8 divided by 4 is 2. And 8 divided by 2 to the third is equal to 1. All right, so let's try and use variables in place of these numbers. So we'll say y is the array size and b is the base. So divide array into 2 halves. So we're always going to binary search always divides stuff in half. So b replaces the 2 in this case. And then x is the number of iterations performed, the power, or the superscript. So what we have, instead of 8 divided by 2 to the third power, we have y divided by b to the x power equals 1. And if you multiply both sides by b to the x, you get y equals b to the x. Looking at our chart over here, y equals b to the x is the exponential form. Now we need to define big O notation in terms of the logarithmic form. So you see here, b to the x equals y. We need to get y by, dang it, b to the x equals y. We need to get x by itself. So we take the log of b multiplied by y. And that's exactly what we see over here. X equals log of b times y. Okay, so we can get rid of the x equals, because we're basically trying to see how many iterations it takes to get to the solution, or to get the value equal to 1. So they just replace that with the big O. And this is log, and b in this case is the 2. We divide by 2. So log 2, and we don't use y, we use n, as we've seen in the past. Now, we don't really, it could be log base 2, it could be log base 10. They don't really care about the base, so the answer becomes O equals log of n. And that took me some time to figure out, so hopefully that makes sense to you. Now, the space complexity is the total amount of memory, and this is O of 1. It doesn't matter how big the array is, definitely not how big the target is, the number in the target. Nothing inside the logic of this solution changes the size of that, so the space will be constant. And that is it. So as always, thanks for watching, and if you have questions, leave them in the comments, and we'll see you next time.